So we're going to continue on with trig. And this unit is all going to be about what the graphs of trig functions look like. Specifically sine and cos. We'll talk a little bit about tan, but not too much. But we're not going to talk about the reciprocal functions. Okay? So it's just a new type of graph. So we'll see what the graphs look like. There's transformations of the graph that we're going to use our knowledge from Unit 1 to help us graph transformations of trig functions. We're going to go the opposite way, find the equation of trig functions given the graphs, and then we're going to go into some problem solving with it, where it can be used. Okay? Sine functions and cosine functions, when you look at the graphs and when we see them, they're called waves, sine waves and cosine waves, because they follow a repeating pattern. Okay? And the name that we give to a graph that follows a repeating pattern is called periodic. Because it repeats itself after a certain period of time. And like I said, sine and cos, they have graphs that look like waves, okay? And any graph that is shaped like a sine or cosine function, we give a specific name. We call it a sinusoidal. I'm just saying. Okay, so what do these graphs look like? So let's look at sine. Best way is to start with a table of values, and the x-axis, or in this case the theta axis, are going to be the angles. And then we're going to find the sine of all the angles and see what pattern it takes. So using your unit circle, and this was a question on the test, what is the sine of 0? 0. So I just plot that. And this is going to be the 1. The sine of pi over 2, using your unit circle. It's a pi 1. Whoa. Stop it. 1. So we'll put it up here. So this is pi over 2, 1. So the notches on the theta axis, we're going to go up by a half pi every time. So I go 0, half pi, and then full pi. And what's the sine of pi? Again, unit circle. Not 1, it's 0. And then when we go up, add another pi over 2, we get 3 pi over 2. And what is the sine of 3 pi over 2? Negative 1. And then we add another pi over 2, so we get 4 pi over 2, or 2 pi. And what's the sine of 2 pi? Back to 0. What's going to happen is this cycle is going to start again. So it's a wave pattern like this, but if we kept going, the next notch, well, when we started at 0 the first time, we then went to 1. So it would go up to 1, and then it would come back down to 0, and then it would come back down to negative 1, and it would keep going on forever, following that wave pattern. And it would go into the negatives forever. Like if we did the sine of negative pi over 2, that's the same as 3 pi over 2, which is negative 1. So it just follows the pattern. Then it comes back to 0, goes back up to 1, comes back down to 0, and keeps going. So you can see it follows a wave pattern.
But it's a chunk, like it's a collection of waves. If I look from here to here, oh, sorry, wrong one. Should be here to here.
Goes like this, and then it goes like this again, and then it goes like this again, and so on.
So this is this is the original pattern here from 0 to 2 pi. So the sine shape is always going to start at the origin, and it's going to go up, down,
Back to where it started. That's what sine looks like. Okay.
and just like we did with other functions in the past and earlier this year,
We did properties. There are certain names or certain properties that are new with sinusoidal functions, certain properties that we've done with other functions, like domain, range, x-intercepts, y-intercept, etc. Okay? So the first one is the amplitude.
before we do the amplitude, we have to know where the midline is of a sinusoidal function. There we go.
The midline
Is the horizontal line that cuts the function in half. So if you look horizontally,
where would I draw a horizontal line so it's equal parts above and below? Where?
why?
You guys, come on.
The x-axis or the beta axis, yes. That's the midline. So the midline, and I think when some of you were saying y equals 0.
The amplitude is the distance from the midline to either the top of the function or the bottom, where it tops out or where it bottoms out.
So here's the midline, here's where it tops out. What's that distance? 1.
So we would say the amplitude is 1. You could have done it
With the negative. We don't say -1 because it's the absolute value. So it would be,
because I just want to know the distance. The distance is 1 to the top or the bottom from the midline. The period of a sinusoidal function is how long it takes horizontally to finish a cycle.
so remember I said when we started here, we went up, back to the midline, down, back to the midline, and then the whole thing started again. So this here is the period, the distance from 0 to 2 pi. So therefore, the period
Would be 2 pi.
because that's how far it is from 0 to 2 pi. Okay, domain and range.
And y-intercept, pretty straightforward. What's the domain, just by looking at the graph?
Yeah, negative, infinity, positive infinity. Or theta equals all real numbers.
What's the range? -1 to
And here,
-1 to 1.
right. -1 to +1. Okay? Or if you use the other notation, it would look like this.
What's the y-intercept? Where does it cross the y-axis? 0.
And you know we can move this.
Why not?
What are you going to do? Right on top of it? Okay. The zeros, remember, zeros means x-intercepts.
What are the x-intercepts?
0, pi, 2 pi, which means it's got to be 3 pi,
4 pi, 5 pi,
-1 pi,
-2 pi, -3 pi, goes forever, right? It's every pi.
So how do we write that? If we're going to write all of it, pi k
No,
ke, not I changed it, remember? Z.
I know what you mean. It's every pi. So think about it. Like here, if k was 0, that means the x-intercept would be 0. That's one of them. If k was 1, that means the x-intercept would be pi. If k was 2, the x-intercept would be 2 pi. If k was -1, the x-intercept would be -pi. If k was -2, -2 pi, etc. So that's the notation to write it. It's happening every pi. Okay? Okay. Let's see what happens with cos. And again, we can set it up the exact same way. Start with the table of values. It will follow a certain cycle. So we can fill in the table of values here using our knowledge of the unit circle. What is the cos of 0? 1. So notice it starts here. It doesn't start here like sine does. What's the cos of pi over 2? 0. Looks like something familiar is happening. Add another pi over 2 to get 2 pi over 2 or pi. What's the cos of pi? -1. What's the cos of 3 pi over 2? Back to 0. And what's the cos of 4 pi over 2 or 2 pi? Same as this one, right? 1. So notice we have another wave, except it started at a different spot on the y-axis. But it still follows the same pattern as sine. And this is the section or period Where the cycle starts and finishes.
So a cosine, remember sine looked like this. Cosine starts up high, bottoms out, and comes back up high.
That's what cosine looks like.
Okay,
What's the midline?
Oh my God. Did it again. What's the midline, the horizontal line that cuts this in half? The x-axis or the theta axis or y equals 0? What's the amplitude? 1. Same as sine. Because this distance is 1. Or if we go from the midline to the bottom, it's also 1.
What's the period? How long does it take to complete a cycle?
2 pi.
Domain and range would be the same as sine, right?
So the domain would be negative infinity to positive infinity, or theta ER. Either notation is fine. The range goes from a bottom of -1 up to +1, or if you write it in the other notation, it looks like this.
Y-intercept?
1.
This one's a little tricky.
The zeros, or the
X-intercepts. You're on the right track. Well, that's the same thing.
Okay, we all agree that this is one of them, right? How much do I have to add to get to the next one? Pi, right? And then I add another pi, another pi, another pi, subtract the pi, subtract the pi, subtract the pi. So I need a starting point for this one. I'm going to say pi over 2 is one of them, and then every pi after that. Both directions.
Positive and negative. You really don't have to worry too much about the zeros. Never really seen much on it. Okay, but it's important just to at least be aware of. Okay? But just notice again, that's another example where if we want notation to represent everything, that's where we introduce K, where K E Z.
Okay.
What happens when we start transforming?
For example, and we're going to look at vertical first. Well, you guys, from your knowledge of transformations, what's happening here?
Remember? If there's a 3 in front of the function. Vertical stretch of 3. Vertical stretch of 1/2. What's happening here? It's flipping. And what it does when it flips over the midline. Okay?
So,
When we have a number in front,
we know it's a vertical stretch by a factor of whatever the absolute value of A is.
we don't include the negative when we talk about stretches, because negatives are flips.
So if it's negative, then it's reflected, in this case, it's reflected in the theta axis or midline. Okay. So let's see what some of these look like.
This one's already been done for you.
This is cos theta. The amplitude is 1, the period is 2 pi, the zeros are pi over 2 plus k, or plus pi k, k e z. The y-intercept is 1, The minimum value, that's the value where it bottoms out, that's at -1. The maximum value is 1. We've already done that. So that's the red one. What happens when we put a 3 in front? It gets vertically stretched by 3. So think of it like this. I'm going to go here. So instead of 1, doesn't it go 3 times its height? So it goes up here. So every time there's a 1, it's up here. Every time there's a -1, it stretches by a factor. We multiply it by 3 and get -3. So we get that, and so on. If it's right on the x-axis or the midline, okay, well, it doesn't stretch anywhere because that's our starting point from where we're stretching from. So if it's already here, it stays here. So it's going to look like that. And now just draw the wave. And that makes sense because it's been stretched 3 times as high and 3 times as low. So what happened here? Well, the midline stays the same, but what happened to the amplitude? What's the amplitude now? 3. The period didn't change, which means that these won't change, the zeros or the x-intercepts. The y-intercept changes though. So does the minimum value. What's the minimum value? And the maximum? Right. So what happened when we put the letter A in front to represent a vertical stretch? It changed the amplitude. So if there's ever a number in front of the function, that's going to be the amplitude. So that's going to be A. So if the function said y equals 5 times sine x, now the amplitude's 5. If the amplitude says y equals half cosine x, what's the amplitude now? It's a half. And we can see this is what happens. So if I look at the original one, it goes up to 1, but half of 1 only gets me there. Half of 1 only gets me there. Half of 1 only gets me there. If I'm at -1, I go half of -1, so -1/2. -1/2 every time there's a -1. The points that are on the x-axis, they don't stretch. So they stay where they are. So it's still the same shape, it's just compressed. Looks like that. So the period didn't change. It didn't stretch out or compress in, which means the zeros didn't change. But the y-intercept changed. So did the minimum and maximum values.
Finally, what happens if there's a negative?
Well, look at the red graph. That's our original. They just flip over the midline or flip over the x-axis. So this point will flip down to here. This point will flip up to here. This point flips down. This point flips up. This point flips down. And the ones that are on the midline, they don't flip anywhere. They stay where they are. Which makes sense, because if you think of taking the red graph and flip it like that. So you're going to get this. So there's no number in front, so the amplitude is no different than the original. It's 1. It didn't stretch horizontally, so the period is still the same as the rest of them, 2 pi, which means that the zeros or x-intercepts are the same. However, the y-intercept has now become -1. The minimum is -1 and the maximum is 1. Same as y equals cos. Okay. Okay. I do want to finish this. Because Mondays and Tuesdays are always a bit of a mess with some of you missing and some of you here, etc. So I want to make sure we're all here for this. The horizontal stretch, that's when there's a number in front of the x inside the function, right? So whatever this is, the stretch is always, like if this was 3, what's the stretch? 1/3, the reciprocal. If this was a half, 2, right? Applies the same way to sinusoidal functions. Okay? So we get a horizontal stretch. By a factor of, now this is a little different, okay? Because remember, 1 period is 2 pi, right? Like we're not going 1, 2, 3, 4, 5 along the x-axis anymore. We're going pi/2, pi, 3 pi/2, 2 pi along the x-axis. So the stretch is actually going to be the period divided by, no negatives, whatever b is. It's not 1/b, it's 2 pi/b. Because if you think about it, y equals sine theta, it starts its cycle again after 2 pi, right? But if I were to stretch it, if this was 2, that means it would stretch a half, so it would stretch back to pi, which is why I have to do 2 pi divided b. This will make sense once we do it now. And if b is less than 0, we flip it the y-axis. It's a horizontal flip. Okay, so I'll be able to explain that 2 pi/b a little bit more. So here's sine theta, the original one we did right at the start. We talked about all this. The amplitude was 1. The length of time it took to repeat a cycle was 2 pi. The zeros were every pi k, where k is an integer. The y-intercept was 0, the minimum value was -1, and the maximum value was 1. We did all those problems. Okay, so what if there was a 2 in front? We should all recognize that's a horizontal stretch of a half, right? So look at it here. If it's 2 pi and it's a horizontal stretch, well, what's half of 2 pi? Pi. So notice I'm taking half of 2 pi. That's why I have to do 2 pi divided 2, or 2 pi, yeah, in this case, 2 pi divided 2. The amplitude doesn't change because it's not stretching this way. So the amplitude is still going to be 1. But the period, and let's start graphing it. So if I start here, let's start at 2 pi. 2 pi and a horizontal stretch of a half takes me here. So it goes from there to there, which means all the points on here move 4 notches left. So this point would move 4 notches left to here. This point, we've already got. This point would move 4 notches left to here, right? Here. So it compresses. Okay? This point moves to here. So notice it all squished in. Okay? So now it's looking like this. Wait a minute. Yeah, that's right.
Why does it go down?
Wait a minute. So half of this. No, you know what? Shoot.
You moved it all over.
Yeah. Yeah, no, I apologize. I'm gonna have to take this out. Shoot. Okay, so let's try this again. So this point, if the stretch is a half of 2 pi, it goes to here. Actually, I'm gonna make this hollow because these are the points I'm gonna use. Half of pi squishes to here. So this point on the original would move to here. Right? Am I doing okay? I think I'm doing okay, aren't I? Okay. This point why am I getting myself confused with this? This point doesn't move. Yeah, so it's going to go like this. Like so. Because notice half. Half of this, half of this takes me here. If it's 2 notches away, half takes me to 1. This one is 4 notches away, it goes to 2. Okay? This one is 6 notches away, it goes to 3, etc. So that's what it does. Sorry about that. That's how it compresses. So this one is, like I said, 6 away, or this one is 1, 2, 3, 4, 5, 6 there. This is 8 away, it goes to there, and then it will continue this pattern. So I'm just going to stop there like that. and then it follows the same pattern on the other side. So this one, if I take half of the x, it goes to here. This one, if I take half of it, it goes to here. This one, if I take half of it, it goes to here. And this one, if I take half of it, it goes to here. There we go. It's going to look like that. Okay. So remember the sine graph looks like this. How long does it now take to complete a period? 1 pi, right? Because this tells me it's a stretch of a half, so I have to take half of this. What are the zeros? Well, it's happening every pi over 2, every half pi. It's hitting the x-axis. So I would put pi over 2k KEZ. The y-intercept doesn't change, neither does the min or max. What's the actual stretch here? 2. So every x doubles. So if I think about it, well, here x is 0, twice 0 stays there. Here, twice this goes to here. This one, remember, I'm looking at the red, not the blue. This one, twice this goes to here, so it really stretches out. This one, sorry, this one stretches out to here. This one stretches out to here. So it's going to look like that. So notice the amplitude is still 1. The amplitude doesn't change. The period, though, how long does it take to complete a cycle now? 4 pi. Because if we continued the graph, we'd get to 4 pi after a cycle. Or, remember, if the period is 2 pi in the original, the period in half would be double that, 4 pi. And there's zeros happening every 2 pi. So 2 pi k, KEZ. These don't change. So a vertical stretch changes the amplitude. It also changes these. But a horizontal stretch changes the 2 columns inside there. And finally, what if we took the red graph and just over the y-axis flipped it? Well, we would get something that looked like this. So here, if I flip that over the y-axis, it stays there. This one flips over to here. This one flips over to here. This one flips over to, make sure I got this right. 6 to 6 flips over to there. This one flips over to here. And then I can go into the negatives and do the horizontal flipping. So this one flips over to here. This one flips over to here. This one flips over to here. So it looks like this.
Notice when we do a flip,
Again. Amplitude's not affected. Y-intercept and these are not affected. The period is still 2 pi. Okay? On a flip. Which means that the zeros will be the same as y equals sine theta kz.
so if there's a number in front, which means a vertical stretch, it affects the amplitude, y-intercept, min, and max. If it's negative, it flips it over the midline, that value of A. B, it stretches it by a factor of 2 pi over B. Okay? And then if you flip horizontally, doesn't change anything. Okay? But we'll practice with these. I just wanted to make sure that we got this done.